This is the module of Intech's Hit the Ground Running training program for vertical helical piers. This presentation will cover the system application, components and options, installation and design of a vertical helical pier. Application and background. Helical piers are a deep foundation element consisting of a steel shaft having welded steel flights that is able to transmit the load from one area to another. Typically, for vertical applications, the loads are transferred from a near surface or shallow foundation level, transmitted structurally through a sensitive or active layer to a geolayer that is sufficiently strong to resist the applied loads. Based on the flighted area of the helical pier, the loads are distributed into a pressure wider than the smaller element. In this way, the helical pier is able to be terminated in a material that isn't as strong as that which would be required for a small diameter end-bearing element. Other names that are commonly used for a helical pier is a screw pile, helical pile, or helical anchor. Another method of installation is horizontal or battered installation. This method of installation is useful for lateral resistance in structural members such as a basement or retaining wall, or to add lateral stability to a vertical element or foundation. These topics will be covered in a separate module. Every helical pile has the following three elements at a minimum: a bearing plate or flights, a central shaft, and some kind of termination. Each of these have different options and configurations that will be covered later in the presentation. The helical flight, as discussed previously, is used to reduce the overall contact pressure by distributing the applied loads. There are typically multiple flights on each pier, depending on the encountered soils and required loads for a project. The central shaft is the element that both transmits the torque during installation and the applied loads through the lifetime of the structure. There are multiple options of shaft type and sizes that have unique characteristics that make them optimal for different soil and loading conditions. Finally, a termination is used to connect the pile to the structure. Two common options are a new construction bracket and a retrofit bracket. However, there are also many other options for termination. Intech can help select the termination that best fits the needs of your project. Feel free to reach out to our business development managers for assistance with determining the optimal components that fit your project. System components and options. In a similar fashion as the three main elements, there are a few components that can be ordered for each helical pier: the termination, extensions, and lead sections. For this presentation, we will cover both new construction and retrofit style piers. Retrofit requires an existing structure to connect to. This slide highlights the three components that can be ordered, with varying options within each component designation. This image shows a new construction, or NC cap as they are often called. The other style of termination that can be used is a retrofit bracket. We will discuss the brackets in more detail later in this presentation. The first component we will discuss in greater detail is the lead section. The lead section is the first flighted section of the pier. Lead sections are named by the plates that are welded onto their shaft. So a lead section that has an 8-inch plate, a 10-inch plate, and a 12-inch plate will be called an 8, 10, 12 lead. Typically, leads have 1 to 3 plates. The more plate area causes more torque to be generated during element installation. The flights are ordered and designed in such a way that make them the most efficient for helical pier use, to minimize soil disturbance and create the best condition possible to allow the soil to support the required loads. At the top of the lead section is a male end connection that has a hole drilled into it for bolting. The next component, an extension, is sleeved over this end, and both are through bolted to allow for continuing the installation of the pier, if required. Another important consideration is that some lead configurations are more common than others. Consult with your local business development manager to make sure that a lead section has high availability that can match up with your project-specific lead times. After the lead section is screwed nearly all the way into the ground, in order to continue advancing the pile deeper, a series of extensions are added to the pile. Based on the loads required for the project, a target torque needs to be achieved. Therefore, extension sections allow for the pile to be extended until a soil is encountered that has enough stiffness or density that gives it the required torque. These extensions are typically unflighted sections of the same shaft material as the lead section. However, short bolt-on extensions are available that can be used to increase the torque drag of the piles during installation that would allow for shortening of the overall pile. These are typically 3 to 4 foot sections of shaft with 1 or 2 14-inch diameter plates welded onto them. Typically, a vertical helical pier can have about 4 to 6 total helical plates on it before installation becomes problematic. The extension sections typically come in 3 foot, 5 foot, 7 foot, or 10 foot sections. The longer 10-foot extensions can be more efficient from a labor efficiency standpoint, but can be heavy and problematic for handling. Depending on the shaft style, they might even require mechanical handling equipment. The extensions have a cold upset female end that slips over the male end of the previous lead section or extension section. Depending on the termination depth, it may be required to terminate the pile with a little excess shaft above grade that needs to be cut off. This would also require drilling a new bolt hole in the shaft of the remaining extension section. Cutting and drilling should be performed in a manner that does not affect the structural integrity of the pile materials surrounding the cuts or holes. Special care should be taken to remove the materials cleanly and in a location that is relatively consistent geometrically with the original location of the hole. The next set of components to discuss are the terminations. The first type of termination I'm going to discuss is for new construction. As you can see, the termination for new construction is a structural steel tube welded to a steel plate. These components are specially designed and rated to a tested capacity. These caps get slipped onto the end of the extension that is cut off at the elevation required to allow for the top of plate to be at a designed elevation. These caps get slipped onto the end of the extension that is cut off at the elevation required to allow for the top of plate to be at a designed elevation. Typically, the structural engineer of record for the pile cap should determine the elevation at which these plates should bear. The ratings of the components for the helicals are typically based on an embedment depth into the pile cap to achieve a fixed head condition. If a pinned head condition is required, it could affect the capacity of the various components of the pile, so this should be communicated. Typically, a minimum 7.5 inches of embedment into the pile cap will be sufficient to achieve a fixed head condition, but this should be evaluated by a structural engineer. The second style of termination I will discuss is retrofit brackets. These brackets are installed to go under the stem wall portion of an existing structure footing. This requires partial demolition of the footing, which will be discussed later. The main components are the bracket body and the T-pipe. The brackets have special design features that make them more useful for special project conditions. These properties should be reviewed, and the correct bracket should be chosen for the project's structural features as well as loading conditions. Another important project scenario that could affect bracket choice would be the amount of structure lifting if required. With these components laid out, another detail that should be discussed is the shaft style. There are two main options for shaft, round and square shaft. The decision of which options of shaft to be selected are dependent upon the loading that will be imparted into the helical element during both installation and completed element lifespan. Each option has specific positive and negative characteristics which should be evaluated on a project-by-project basis. The first option we will discuss is square shaft. The square shaft is the more cost-effective option and is typically the first choice that should be considered. Square shaft is great for creating the most cost-effective element, is able to penetrate into more stiff and denser materials than round shaft, and can structurally transmit loads effectively through materials that are not soft. Some scenarios which square shaft is less suited for would be when a lateral load or moment are intended to be applied to the helical shaft, when a section of the pile will be unbraced creating a buckling concern, or when there are thick layers or shallow layers of soft soils in the profile creating a buckling concern. In these conditions, it may be necessary to choose a different pile configuration, which I will discuss further in the presentation. The naming convention for the square shaft element starts with a two-letter combination SS, which stands for square shaft. Following the square shaft designation is 1 to 3 numbers, which is intended to represent the square dimension of the shaft. So SS125 is a square 1.25 inch by 1.25 inch round corner square shaft. One special consideration for this naming convention is that both SS5 and SS150 are 1.5 inch square bar dimensions. The difference between the two is that the SS150 has a higher strength steel which allows for more torque and structural capacity. Additional engineering properties specific to each bar type can be found in the Chance Technical Design Manual. This table represents some general ratings for the shaft lines. It is important that in order to create the most cost-effective element, that the elements are spaced in a way that maximizes the capacity of the pile. It is generally efficient to try to match up the element spacing to result in pile loads that are close to the shaft's max capacity. Some soil scenarios, such as gravelly or cobbly profiles, may require the opposite approach to be taken to account for localized spots of increased torque required to penetrate them. The second option of bare steel shaft is round shaft. This type of shaft is less cost efficient than the square shaft materials, but has better properties in certain loading scenarios. Typically, these shafts are selected when there is a concern for lateral loads or moments, unbraced length concerns such as exposed pipe shaft or soft materials. These shafts also have less efficient torque to capacity ratios when compared to square shaft. Additionally, there can be concerns with penetrating into denser materials compared to square shaft. This will be addressed later. The naming convention for round shaft is related to the pipe dimensions. The name begins with an RS designation, which stands for round shaft. Following that, a 4-numbered designation is related to the outside diameter of the pipe. Then, after a period, there is a 3-number designation that identifies the wall thickness. Therefore, an RS 2875.203 element will have a round pipe having an outside diameter of 2.875 inches and a wall thickness of 0.203 inches. There is also a high-capacity pile, which is a limited service pipe having higher strength properties. Additional engineering properties of each shaft type can be found in the Chance Technical Design Manual. Similar to before, it is important to try and match up the element spacing to maximize product capacity. However, as round shaft is typically selected based on special conditions, it may be necessary to oversize the pipe based on structural buckling or bending concerns. Now that we've discussed the 2 bare shaft options, we will discuss some special configuration options that we can have access to as well. The first special configuration that I will discuss is a grouted helical. This element consists of a standard square shaft helical that also has a grout column pulled down by gravity during pile advancement. The grout pile diameters typically vary from about 4 to 7 inches. The pile is created by the addition of what is called a lead displacement plate, which is a circular plate with 2 paddles that creates an annulus in the soil. Additional components called extension displacement plates are added to each extension section and are intended to verify that the hole stays open throughout the installation. Casing can also be added to the system and can be advanced by the drill string without having to utilize extra pieces of equipment. The grout column adds additional structural resistance and also allows for additional geotechnical resistance to be developed with depth. This creates a combination frictional and end-bearing element. An increase of about 50% of pile capacity when compared to a bare helical has been observed to be a practical rule of thumb. However, this will be dependent upon the soils and can be more or less. An important note is that the composite system also increases the structural capacity of the pile and compression. However, the steel components will still control in tension capacity. The second special configuration that can be used is a combination pile. These elements start with a square shaft lead section and possibly some square shaft extension sections. At this point, a transition coupler is used to switch to round shaft extensions. The remaining pile is advanced using these round shaft extensions. With this type of configuration, it is possible to have the benefits of square shaft at the lead section and leave round shaft up high on the pile to alleviate concerns such as lateral loads or buckling. These couplers also are through bolted so that they can transfer tension loads. The third configuration is drive cast. This is a large diameter round shaft pipe that has a series of displacement assemblies that creates a large diameter annulus, typically 8 to 14 inches in diameter. Grout is pulled down into this annulus by gravity as the pile is advanced, which creates a large diameter grouted steel element. Typically, the elements are limited to about 40 feet and require pre-drilling in dense materials, but they are very useful for obtaining very large capacities depending on the soil conditions. The structural section of the elements are also very strong compared to the smaller diameter non-grouted round shaft elements or the grouted square shaft helicals. An additional lead section option is rocket leads. These are a stronger version of the typical lead sections that also have a carbide tip cutter for tearing through problematic gravelly, cobbly soils, dense soils, or even some rock formations. These can be utilized to reduce chances of spin out, which is when the pile turns without advancing. This condition results in poor pile performance. As discussed earlier, there are a myriad of various pile terminations available. Shown here are a number of the more common ones, including tieback terminations, slab brackets, porch brackets, boardwalk brackets, and shackles. We have experienced business development managers who have a great understanding of the product offerings and availability of different components. If you have a special project termination need, feel free to reach out to us at any time, and we will help you select the best option for termination to support your project. System installation. Before we go into the actual element installation, I will discuss the different types of equipment that can be used to install helicals. First, I will go over the typical components for a handheld installation. To install by hand requires a power source, such as a hydraulic power unit, a valve system to control hydraulic fluid flow, hydraulic hoses, a drive head, and torque bar. There are various styles of drive head that should be selected based on their torque rating. Additionally, a hydraulic power unit should also be selected to have sufficient flow and pressure to give enough power to the drive head to get to its maximum torque. This style of installation is typically limited in element capacity that can be achieved, but is usually adequately sized for residential element installation or light commercial structures. This equipment can also be used in tight, hard-to-access locations such as basements. The second style of installation is using an excavator or skid steer. This installation is typically for higher capacity piles, but can also be used to install lighter piles if needed. There are special mounts or adapters that are equipment specific that hook the drive head up to the equipment. If the equipment has hydraulic fluid capability, it can be used to power the drive head. As before, the equipment should have sufficient pressure and flow that can meet the needs of the drive head to achieve maximum torque. The drill string is the portion of the setup between the excavator and the helical element. The first component, at the top, is the drive head, which is the drill. There are a number of manufacturers and sizing for these with specific torque and efficiency ratings. Attached to the drive head is the Kelly bar adapter, which slips onto the drive head and bolts to the torque monitor. The torque monitor shown directly measures the torque imparted through the drill string. There are other methods of torque monitoring that are available. However, this digital style of torque monitor is the most recommended method of monitoring. Then, a drive tool bolts to the torque monitor, which then gets slipped over and pinned to the shaft of the helical element. Now I will go through an example installation for a retrofit pile and then an example installation of a new construction pile. The first type of installation I'll cover is a retrofit installation. This is when an existing structure needs to be underpinned. First, a pile location is selected and the soil should be excavated to under the footing. Once the soil is excavated, the foundation should be partially demolished up to the stem wall portion of the footing. It's important to try and get this demolition to be clean and neat, with a special emphasis on squareness of the face and under the stem wall. Selecting the right tools for the project are also an important means of making sure that the demolition goes smoothly and efficiently. Once the demolition is completed, place the helical lead section into the bottom of the hole. Slip the drill string over the pile lead shaft and pin it together. At this point, it may be necessary to hold the lead section at a slight angle to get the helical flights under the footing. At completion, it is intended for the pile to be at an approximate angle of 3 to 5 degrees from vertical, but the angle may be more horizontal at the start of the element installation. This means that the lead sections will be extending under the structure that you're underpinning. The helical lead section is spun with the drive head while applying crowd with either the weight of the equipment or using a come-along. If sufficient crowd is not applied, the piles may spin without advancing, called spin-out, which we discussed previously. Once the lead section is nearly all the way into the ground, disconnect it from the drive head, add an extension, and reattach to the drive head. Advance the lead section and extension section until it is nearly into the ground. Repeat this process until a target torque or depth is achieved. At this point, it may be necessary to cut off some extra shaft. This can be done with the bandsaw. Cut off the pile at a height where the bracket will seat and pick up the foundation. Now you can add the lifting setup. Here's a closer view of the lifting setup. For the lifting setup, the intent is to pick up the building off of the pile section a specific amount, and then lock off that lift using thread bars and nuts. Typically, a minimum lift is targeted as it will have less chance of negative impact on the existing structure. Lifting a building beyond a very minimal amount should be performed by an experienced installer. The minimal lift engages the structure's loads with the piles and helps transfer the loads to the lead section plates of the pile. At this point, installation is completed. The second style of an element installation that we'll describe is a new construction element. Typically, a footing is excavated prior to arrival on the site or prior to element installation. Similar to the retrofit installation, the element lead section is placed into the hole and the drive head assembly is then connected to the top of the lead section. The pile is advanced by applying crowd and torque to the pile. For new construction, vertical piles are intended to be installed at a near vertical angle with a slight tolerance. This is different than for the retrofit pile, which was intended to be installed at a slightly battered angle of around 3 to 5 degrees by design. As before, once the lead section has been advanced nearly all the way into the ground, the pile is disconnected, an extension is added, then the drive head is reconnected. At this point, the pile is then advanced in the same manner as before. Crowd and torque should be maintained to minimize spin-out. Once the pile achieves the target torque or depth for design, the excess pile shaft should be cut off and the pile cap should be attached. If required, bolts may be installed into the pile cap for tension capacity. This may also require drilling a new hole into the shaft that has been partially cut off. As discussed previously, this procedure should be done with great care as to not affect the strength of the steel. The whole element termination will then be cast into the footing or pile cap for the structure. There are a few important notes that should be understood throughout installation, and they are listed here. A very important concept for helicals is the fact that they should be screwed into the ground as opposed to being drilled into the ground. The soil should be moved out of the way, but not removed from the hole. If the soils are removed, that creates disturbance and a lack of confinement, which can result in poor pile performance. Second, the crowd should be applied to the pile during installation so that the pile can penetrate the materials. This can have an impact on the installability of a pile from a standpoint of how heavy your excavator is or how much crowd you can reasonably apply with a come-along. Third, the rate of spinning should be slow enough to allow for this screwing style of installation. Coupled with this is spin-out, where you create a high level of disturbance within a zone that can result in system failure. Finally, another important concept for these piles is that if a load test for resistance verification of a pile configuration is required, the load test should be performed prior to the installation of the production piles. If you install the majority of the piles before a load test, and then the load test verifies that the depth and lead configuration you installed them to isn't good enough to withstand the loads, it may require removal and/or reinstallation of the piles. One of the more common forms of special configurations is the grouted helical, as discussed before. As it is a more common option, we will now describe the general method of installation. First, as with a regular helical element, you set up and install your lead section. You do this by applying some crowd with your equipment and applying torque with your drive head. This pushes down and screws your lead section into the ground, and you do this until a portion of the bar is sticking up out of the ground. Next, you install your lead displacement plate, the one with the paddles, and an extension. You also want to set up a grout reservoir that will hold the grout throughout your installation. We usually see this being done with just a sonotube. It needs to hold enough grout to where you're not constantly filling it up, but not enough where you spill out excess grout at the end of the element. Another note, you will likely need to bury the reservoir a little bit or seal it at the bottom so grout doesn't come out. So with the grout reservoir filled, the next step is to start advancing your element, applying crowd and torque. The extension displacement plates and extensions should be added as necessary as the configuration penetrates the ground. Also make sure to maintain your grout head during pile advancement. The lead plate will create an annulus that you should fill in with grout. Keep doing the same, applying crowd and torque, adding plates and extensions as necessary. The lead plate creates the hole and the extension plates maintains its diameter. Once depth or torque is achieved, you can cut off excess shaft and terminate it with a pile cap. It is important to note, as these elements are both frictional and end-bearing elements, it may be necessary to double-check that the installed pile meets your design criteria. If the pile achieves torque sooner than intended, it may mean you have less frictional resistance than you planned for in your design. Based on this, it should be checked that the steel helical can take on the remaining load. These elements are typically load tested to verify that the combination of skin friction and lead section resistance are adequate. The foundation contractor will cast the termination into the footing. It is important for design to have the cap in a spot that doesn't interfere with other reinforcing in the pile cap. That'll ultimately be on the structural engineer of record for the footings though. So here's a completed element with each of the components that we discussed. You will note that a completed element consists of a steel square shaft element with a pulled down grout column. System design. Here's a representation of the general workflow for most projects. An important part of this workflow for retrofit elements is to determine the structural condition of the existing structure. Sometimes a structure may not be in good enough condition to withstand wide spacings. As a general rule of thumb, 3 to 5 foot center-to-center element spacings are typical for a foundation that doesn't have very much section or is slightly deteriorated. This should be evaluated in person by a structural engineer, and additional information regarding spacings with different types of foundation configurations can be found in the Chance Technical Design Manual. The major component that drives the geotechnical strength of the system is the end bearing capacity at the plates of the lead section. In order to determine when to stop advancing a helical, there are a few metrics that can be utilized. Namely, you can install an element and subsequently load test it, or you can monitor torque during element installation and compare that with empirical values of torque to capacity ratios that have been thoroughly researched by Chance. We will discuss this relationship further in the presentation. An important note is that an underpinning system can be installed that works geotechnically and structurally for the pile, but does not work structurally for the building. The existing structure should be able to resist the intended spans of the elements as discussed previously. Two references for estimating the structural and geotechnical requirements on a pile are the Chance Technical Design Manual and Chance's software package called Helicals. Here are a few sections of the Technical Design Manual that can be very useful for designing the elements, including worked out problem sections. Additionally, the Guideline for Designer section has some example specifications that outline what the requirements for an element should consider. And finally, Chance has published a number of Helicals tutorial videos on their website at this hyperlink. One design principle analogy that helps understand the design principles is screwing a screw into different types of wood. In a manner of speaking, we can think about dense or stiff soils being analogous to a harder wood like oak. On the other end of the spectrum, we can consider a soft soil condition to be more analogous to softwood like pine. When you think about these two scenarios, a few intuitive relationships can be assessed. First, if you install a screw into each of the two conditions, it will require more torque to install the screws into the harder wood than the softwood. After the screw is installed, you would then assume that it would be more difficult to pull the screw out of the harder wood than the softer wood. And finally, you would think that if you tried to push the head of the screw sideways while it's in the wood, that the softwood would give away more readily than the hardwood. A lot of these same principles can be observed with installing a helical element into either soft or stiff soils. So, taking these principles and applying them to helical anchors, a relationship develops between the pile's capacity and torque. Through an immense amount of historical torque installation monitoring and load testing, Chance has developed a set of what is referred to as torque correlation factors or KT values for each shaft type that are recommended for design. As you may notice, the torque correlation factor for all square shaft elements is 10 foot to the minus 1. For the round shaft elements, the torque correlation factor varies depending on the shaft diameter. I will discuss why these relationships aren't the same later in the presentation. One thing to note is that these values are empirical. They can be slightly over-conservative depending on the actual soils at the project site. The only way to truly test the capacity of a specific pile at a site is to load test it. A load test can be used to create a site's soil-specific relationship between the torque and capacity. This would help create a customized, more efficient torque correlation factor that can help save money. So rearranging that relationship can be helpful depending on what part of the project you're doing. As an installation contractor, it can be helpful to determine what torque you need to achieve during pile installation. The second installation lets the contractor, who's given a load, the ability to figure out the required torque for an element. So as a quick design example, the engineer calls out that they need a 20 kip pile, with a kip being 1,000 pound increments. Based on this, assuming the site is conducive to a square shaft element, you divide the required ultimate required capacity, which is the design load with an applied factor of safety, by the torque correlation factor. So with a torque correlation factor of 10 foot to the minus 1, the required torque is approximately 2,000 foot-pounds. As a second design example, if the engineer realizes that there is a buckling concern and the pile section needs to be changed to a round shaft anchor and upsized to a 3.5-inch shaft, this changes the torque correlation. With a shaft-specific torque correlation factor of 7 feet to the -1, the required torque for the element increases to 2,850 foot-pounds. So the difference between the two highlights the increased torque that is required for the same load capacity between the two shaft types. The main reason why there's a difference in how torque relates to capacity between the two shaft types is how these shafts are interacting with the ground during installation. For a round shaft, shown on the left, you can see a cross-section of the pile with the hole it is creating. The outside diameter of the shaft is in constant contact with the hole, and this happens through the majority of the pile length. On the right, you can see the square shaft cross-section and how only a few small points are in contact with the hole. So, throughout installation, torque is developed between the helical components and the ground. This happens in both the lead section with the plates penetrating the soils, but also happens between the soils and the shaft. Based on the limited amount of contact between a square shaft and the soils, most of the torque that is generated during installation is only in the lead section in the plates. For the round shaft, however, there can be quite a bit of torque generated by the shaft, which affects that relationship. As the pile shaft diameter increases, there is more surface area that is in contact with the soil, which is why that relationship decreases with increase in round shaft diameter. The general design for a helical element consists of a few parts. The ultimate bearing capacity for each plate in a configuration is calculated with depth. Then, based on the torque correlation factor for the shaft type, a capacity with depth can be estimated. Finally, considering this and the structural capacity of each individual element, the lesser capacity of the two is selected and provided as the recommended capacity in HeliCap. An additional note that can be important is that the shaft needs to be sized in such a way that it can overcome the torques required during installation. And finally, the pile settlement can be estimated using some assumptions with stress path, but this is beyond the scope of this presentation. Typically, observed deflections for elements installed using the empirical torque correlation factors is on the order of 1/4 to 1/2 inch. This can be verified on-site with a load test. The Chance Technical Design Manual has a number of design examples for helicals in different scenarios. These can be reviewed and include a number of references and additional information. With every quote that we complete, we look to have the following information. These are the typical parts that, as a distributor, we are looking to put together for our quotes. In order to accurately estimate a pile that will work, there are a few major things that we need to know about. First, a major piece of information that helps us create a more accurate representation of how the soils will react to the load is a geotechnical report with strength information. Typically, these reports are performed by a geotechnical consultant and include drilling, blow counts, lab testing. Another means of determining soil strength conditions with depth would be to install a test helical element and record the torque required to install it. This information can then be used to create a soil strength profile. The next piece of information that is needed is the loading scenario. This would be the compression, tension, and any other lateral or moment loadings that need to be resisted by the pile. These are structure dependent and are usually identified by the structural engineer of record for a project. If a pile's spacing is not initially determined, another good way to have this information presented would be the intended load per linear length of footing. With this, different spacings can be tried to iteratively determine a cost-efficient pile, including lead section, configuration, and length. Finally, the last piece of information needed is any special types of project-specific conditions that could impact pile performance. Things such as above-grade height or intended termination should be communicated. For a design submittal, these are the general pieces of the puzzle that should be completed or determined prior to the element installation. Main takeaways. To conclude this module of the presentation, the following topics can be reviewed as major points. The ability for a helical pile to provide resistance is a function of the loads and geotechnical materials at each site. This presentation was intended to be an overview of the major principles for design, installation, and element options available. This presentation should not be relied on solely for design. For more in-depth explanation of the system and design examples, the Chance Technical Design Manual can be referenced.